My name is Characterisation. I'm from the University of Porto. I bring up preliminary results about this idea of trying to using optimal control and to characterize the switching times between stages. We address the simplest problem, the one that comprises the real out and then the real in phases. Okay? But before I start, let me take the opportunity to present to you all our upwind project. Okay? So we started looking into this subject of airborne wind energy in 2015. Okay, then we got funded from national funds in 2018 with the project with the same name, upwind. And recently, in 2022, we got two national projects funded. One in upwind atoll, as the name is indicating. The idea is to focus in autonomous takeoff and landing, such as you saw earlier in Sergio's talk. And also the second one is about airborne wind energy farms, okay, as you saw in Louis' presentation. Okay. That's our website, is not updated, but we hope to do it as soon as we can, okay. And this is our team, 4 senior researchers, 3 PhD students, and at least 5 master students, all working in airborne wind energy. Okay? So, our research interests are, of course, optimization-based control, model-predictive control, path planning and path following, kite farms optimization, renewable energy, and of course, airborne wind energy. Okay. Just bear in mind our symbol over here. You see, upwind, because if you see, we have a soft kite over there, but we at some point take the step for ground jam fixed. Okay? So our system, you already saw a picture in the previous presentations, but it's a system like this with a glider. Okay, and now let me go into this idea of hybrid optimal control. I already also heard about it in this morning, I believe. So what is hybrid optimal control, or also called optimal multiprocess problems, are a certain class of problems that involve an optimization of multi-phase control problems. And the simplest case involves a 2-phase control problems in which 2 different sequential control systems are linked over a specific period of time. And it seems to us that this is the perfect case to apply to airborne wind energy. So the idea is to maximize the average power production of a 2-phase full cycle and make time decision variable, and I will get into that in a moment. Okay? So how do we start this? We start by formulating an optimal control problem in the typical way, using objective function or a cost function, then subject to dynamic constraints and initial constraints, some final constraints, okay, over the states and over the inputs, okay. In this simple case, we might define our cost function as the maximizing power production, okay. Then we have a second problem, the retraction phase problem. In this case, we have again to minimize a certain objective function, again with dynamic constraints and input and state constraints. What I want to stress out in this slide is that you can have a different objective function that is different from the previous problem or the first problem. You can have also different dynamic constraints, and of course you can get this initial state constraints and final state constraints also different from the previous problem. Nevertheless, we just have to guarantee that the initial condition in this second problem is just the same or coincide with the final condition of the previous problem. Okay? So, as I said, we have to reformulate this problem as a one single fixed time optimization, optimal control problem. And what we do is a time transformation to redefine the states and controls as new states and controls, taking values in the same time interval that is all to one. Okay. So in that case, we got this single optimal control problem. We have now to minimize different objective function, but of course it's somehow a combination of the two previous ones, of the two previous problems. Okay. The constraints are changed because we have to do this time transformation. If you notice here, we have this tau1 and this difference between tau1 and tau2. There is the time, let's say, intervention of the first objective function and then the second intervention of the second objective function. Okay? In this case, now we have the full problem, the full production problem, or the full cycle, let's say, complete as a single optimal control problem. Okay, these results are quite preliminary. Okay, we just got them last night almost. Okay, so please be all in Madrid to see better results. Okay. Let me just concretize some aspects. So the traction phase, our objective function is to maximize power production. Okay. In our retraction phase is to minimize power consumption. We already saw tried to solve this problem in the second phase, the retraction phase, as a minimum time problem. The idea was to reel in the feather as fast as we could in terms of time. Okay. We decided to keep the kite dynamic constraints equal in both first and second problems. The same with the input constraints, but then we could not do the same with state constraints because we want, in our reel-out phase, we want the kite to produce in such a way that is almost in crosswind, but then to reel out back the cable, we have to put it in a zenith position, and so we have to allow, let's say, the elevation angle to be higher than we can allow in the first one. Okay? That's one of the reasons that we have to do this. We have to change effectively the state constraints. Okay. The models and other conditions you can see on this, if you are interested on these two references. Okay. And what is the big challenge here is to numerically solve a more complex problem. Okay. So we started with two not so easy problems to solve, and now we have a bigger one to solve. Okay, that's the main challenge here. And then, of course, we would like to use this online, which is quite impossible. So we have to solve a set of problems varying the wind conditions, and then use a table online to use it out in our account. Okay. What we use in terms of software is we use iClock's interface, that is the Imperial College of London optimal control software. Okay, we are also already working with Casadi, but at this point is ongoing work. At least two of our master students are looking into it. Okay, and then we use as a solver to this problem the IP-opt, and also trying to use this warp solver, because since the problem becomes bigger with more variables, at least warp stands for we optimize real huge problems. So let us see if that's true, and maybe in Madrid I can check it if we get some good results with it. Okay? So this is, like I said, preliminary results. We have here in green, like the shape of the code in the flight envelope, okay? And then you see the kite doing these circles or elliptical shape trajectory, and in the end it turns into this reeling phase, this blue line, okay? And we actually did it and solved the problem. Some ideas for the future is to add on extra phases like the transition phases, okay? And of course this will bring another complexity to the problem. That's why we are doing it stage by stage, but let's say that we started with these two phases problem, but now we tend to do more than that, okay? We can also consider some different dynamics in different phases. We are thinking about that. We will also apply some optimality conditions analysis to see. And we can add a more complex theta model to the problem, okay? I think I didn't quite pass the message that time being a decision variable will be quite interesting to us to know if we should start the wheeling phase before we get to the maximum theta. I believe that all systems, at least for now, will be in the wheel out phase until they get to the maximum theta length, and only then they start wheeling in. But we are now considering the cable drag, and we are now trying to see at which time is the theta has a significant contribution to the system, and then maybe it's is the best for us to really back the cable instead of continuous wheeling out until we get reach the theta, the maximum theta. Okay, so thank you very much.
Thank you, Louis, for this interesting talk. I'm not so sure now, but I do think that the tether length is a parameter in some of the optimization problems that we have. So it's not that you always reel out to maximum length. It is a parameter that the model chooses to get maximum power per cycle. But I think
we think that maybe we can find that optimal time to reel in.
Yes. Yeah.
In that sense.
Yeah. Are there any questions from the audience? Yes.
Thank you for the presentation. It's not on.
I can listen. Yeah.
Okay, I
You
can
can
speak
talk,
up.
yeah.
I saw that in some of your slides, thank you, since it's such a complex thing to solve in the hybrid optimal control solution, I'm guessing you're using dynamic programming, right?
No. We are using direct communication.
Because I saw that there was a mesh refinement source that you quoted to improve
Yes,
the solution.
yes, in the path we did that, but for the wheel out problem. Okay. We are not. We may introduce this mesh refinement strategy in this bigger problem, but for now we are just interested in solving it with some tools that are available.
Okay.
Okay. Yeah, but we are using direct methods, but not dynamic programming.
That might be an interesting solution because of the boundary lines that you can introduce to dynamic programming to improve drastically the solution and reduce the time calculation.
Yes. Thank you.
Are there any other questions? No, then thank you again.